slabs sticking down into the mantle. Those cannot migrate laterally very fast at all. And the plate has been locked between those two Benioff zones at least since Paleocene and probably even Campanian time. So the relative motion is driven by the westward drift of the Americas. And this piece of Pacific crust just overrides the oceanic portion of the Americas, sitting between North America and South America, while the two continents go past. And what it means for North and South America is this oblique collision, which has come from the west-northwest and progressed across Venezuela, first northern Colombia, this is Guajira, then across Maracaibo, the Caracas segment, Serranía del Interior, and eventually Trinidad, just off the page over there. So that's Eocene. It's going to keep coming through the Oligocene. And you can imagine some of the river systems coming down this foreland axis. It looks a lot like the Middle East, basically the Persian Gulf here. You can imagine rivers like the Tigris and the Euphrates filling depot centers just out in this area here, some of which I think must sit in Barbados today. Just how it got there is still an active question for research. But the sandstones over there are beautiful. They're about 97% quartz, and they are early and middle Eocene in age according to pollen. There's no late Eocene age yet known. And that makes it very suspicious that it is the down dip equivalent of Mizoa types of sands over in Lake Maracaibo. Right, so the plate keeps coming, and by about earliest part of Middle Miocene or latest part of early Miocene, we start to see the Kanapo conglomerates. And these are coming down from the northwest. They are pebbles comprising argillite. There's manjack in here, as well as detrital-clast, which means that maturation is underway by early Miocene time, coming to the surface and being reworked into the basin. Most of these rocks are very happy to have come from the Serranía del Interior. They don't need a local origin. All the rocks in here that you can see as pebbles, you can easily relate to the stratigraphy in the Serranía. So it means that the oblique collision has reached the Serranía del Interior. It's up and providing detritus toward the southeast into the Trinidadian depot center, just as Philip Farfan and Bob Ehrlich said about 20 years ago now. Now some of these rocks seem to be making it all the way to the south coast. And this is at Galfa Point. It's a place we'll be going tomorrow on the field trip. It's a conglomerate that has the same constituents in it as the Kanapo, and as far as I'm concerned, these are simply farther traveled sands that have come across the shelf that we call the Brazo Shelf down into the remaining basin at the foot of the fold thrust belt. And there's an unclosed basin to the south of Trinidad for the end of Middle Miocene time. You could call these Herrera if you want. The sandstone that it's sitting on is probably also Herrera, and it's saturated in oil. And these are both from that point. So a 12 million year map would look something like this. Now the collision has come across, and there's the fold thrust belt developing across here. Southern basin of Trinidad is sitting here, and we have big strike slip systems yet to assemble the pieces of Trinidad from west to east, and that's going to be the bulk of the remaining part of the talk. And you can see I've put the northern range, which belongs right here. At this point, it's back nearly 220 kilometers, assuming about 20 kilometers per million years of relative shear. I'm one of the guys who doesn't like the idea of a whole lot of strike slip motion across the northern fault zone, although at this point we were still drawing it. This is a 2002 map. But certainly after this time, after 12 million years, there's not a lot of information that you could use to prove active strike slip faulting. Yes, the rocks are broken, as I'll show you, but it doesn't look like a through-going strike slip fault to me. So anyway, here's the erosional source in white. It looks like a dolphin's head, and the fans are coming down this way, Kanapo in this fringe, and then the Brazo Shelf into the deeper water down in through here. And some of these fans we would call the Herreras, I think. And then everything changes. In about 10 or 12 million years, the compression, for whatever reason, really does look like it turns off. And this is just a collection of seismic lines from the north of Carúpano over here, from Venezuela. The important line to note is this heavy blue dashed line. There's lots of signs of compression underneath it in almost all these sections, but itself, it's a peneplain, an erosional peneplain. It was probably subaerial in a lot of these areas that are shallow anyway. And then if you look above it, all the deformation is almost entirely extensional. So the collision that was underway and happily producing an orogenic front that provided huge quantities of plastics to the southeast, for some reason turns itself off. We need an explanation for that. We can also go into the Foreland Basin, and this is from a paper by Borger back in 1952, and even in the Maturin Basin, we see the same unconformity as far as we can tell. It's the same age. We have early and middle Miocene on top of the rest of the Cretaceous section and Paleogene section in here. Peneplain flat, and then above that, nothing but extensional faults. There's no more compression in this basin. However, there is ongoing sedimentation in terms of these formations above the Kiri sandstone and conglomerate in through here, which is itself a big reservoir. And then altogether about 10,000 feet of La Mesa and Pica Pica, but no compressive deformation in it. So something really drastic happened at that time. It also applies to Trinidad, it applies to Columbus Basin, it applies to the area around Margarita, and so on and so forth, even out to possibly even Barbados. So there's a big event, and in Trinidad we have some of the seismic sections that we have interpreted from the Exxon data set. Again, the culmination of the deformation seems to have taken place at about 10, and then on top of that we see mainly extensional types of deformation. And we have an erosional unconformity across a lot of the origin, which has been formed by 12 or 10 million years. And then above that is mostly extensional types of faulting and the return to sedimentation after the erosional unconformity had cut down. So something needs to change. And I came across this slide this morning just looking for things to include in the talk. And it's a bit of a historic slide for me because it's one I coupled together back in about mid-90s, I think, 1994 maybe. And I was onto this problem about the 10 million year unconformity back then and trying to find ways to understand it. And what I compiled these 4 sections in through here. B is this one. Here's the top of the 10 million year erosion surface, and that's the fold thrust belt that is the Sernia del Interior. And then there's the erosional surface, and then this half-graben looking geometry there that goes back underneath the frontal thrust of the Alachthon. And you can see the growth on that, and it really does look like the mountain front pulls itself away again, and in a rotational sense, with an onlap up the face of the mountain front. And then above that is a time when some of the internal reflectors in here look like there's compression going back on again. And we go to these other sections, and again it's the same thing. Guarapichi in C. We have an erosional unconformity in through here, and it looks like the whole thing slipped back to the north, a rotational onlap, and then we see the growth associated with renewed compression associated with Pedernales in here. Same thing in Paria, half-graben looking thing with what could be taken as a listric curved thrust front that's backing off, asymmetric wedge with onlap, and then the upper section in yellow showing growth again up the compressive feature in the southern side of Gulf of Paria. And over in Crony Basin, this is a little bit different, but still the same general idea going on here from the north. We have an erosional unconformity that we know we have 10 million year metamorphics under there. It looks like it collapsed again, and there's the onlap to the north, and then the growth section on top of that. So whatever happened is really, really significant because the tectonics changed quite a lot. So the idea that we formulated back then was that there was a middle Miocene in placement of frontal thrust systems. That led to subaerial exposure of this really large, broad area. And then there was a relaxation in the late Miocene that led to renewed deposition on top of the erosional unconformity. It's generally associated with extensional faults. The formations we're talking about are Manzanilla, Cruz, things like that. So that's the renewed deposition. In comes the Orinoco. It comes down this trough to get out to the sea, and you know that story quite well. And then in the Pleistocene, the whole thing inverts again, and the half-graben looks as though it inverts, and we get these, the uplift of the southern anticline all across that whole southern lip of the origin. And we can see the growth in the reflectors as it goes up. So that was, so to make a long story short, I mean, it looks from that data that we had a middle Miocene compression, and then from 10 to about 3 or 4 million years, we had this transtensional phase. And then since 4 million years, perhaps the direction didn't change, but something has changed at about 2 or 3 or 4 million years, and we'll come back to that. There may be a change in direction in these two layers, or perhaps the eastward motion is trying to climb obliquely up the basement morphology that actually tilts off to the northwest, and that could give a compression across the whole region again. And I think that's probably where we're at the moment. So the relative motion history, you've seen me present this before, but from my work in the Northern Caribbean during thesis days, I had realized then that there must have been a kink in the relative motion vector for North America Caribbean in order for the Puerto Rican forearc to get around the Bahamas Bank and out to where dredges have proven the existence of arc basement there, as opposed to having climbed right over the top of the Bahamas. So I think we had this idea before we came in here, and it seemed to hold up in the southern margin as well. So oblique collision to about 10, switching to strike slip. So for me, the whole eastern Venezuela, Trinidad area became a right lateral simple shear system for the last 10 to 12 million years, rather than an oblique collision. Now that is a little bit semantic, because a dextral shear system will produce a bow wave, which is compressional, and some folds could be sort of sent off in the southeastward direction, trying to get out of the way of the curvilinear shape of the Caribbean plate as it continues to move. So whether you call that collision or simple shear, hard to say. It's a bit semantic, but the point is, on the side of the boat, after you get around the side of the Caribbean plate, where the edge of the Caribbean plate is east-west, there's no more compression. That's where it's turned off. So I think the bow wave is actually quite a good analogy. And we worked with that for about 10 years, and then finally the GPS came out, and it was obvious that the east-west relative motion was correct. So that means that about 10 years of work was still valid. Hadn't changed it. So I'm going to now, so that's sort of an introduction to what I think we have to work around. I really can't see that any of those things changing very much. And now let's think about Gulf of Paria, North Coast Fault Zone, and maybe some of the strikes and faults where they pass off the eastern side of the island as well. So this is a line from the North Coast Fault Zone. It comes out of our program. It's a computer scan of a real seismic line. But you can see the top of the northern range is coming down through here. And yes, there are a few tiny little faults, but they're trivial, and they are not the plate boundary. Okay, I think we'd all have to agree with that and accept that. There's perhaps a few hundred feet of sort of a graben-looking feature in through here that might be the 10 million year unconformity, or maybe the top of basement, I'm not sure. But it's not a very significant set of deformation features. If we go over farther to the east, this is probably the northern range equivalent, and the Tobago basement comes up in through here. Yes, there's a normal fault, and maybe a few, an array of normal faults in through here, but at least at the top, the young strata seems to go right over the top, and it's certainly not an active plate boundary at the present time, although prior to 10, I couldn't say no. So let's just take it at that. It could have been an important fault zone prior to 10, and it probably was, because we need ways to get the metamorphics up at that time. And then we go over here at the Dragon's Mouth, and we can see the section coming up onto the northern face of the northern range. And yeah, there's a fault zone, and maybe even a little diapirism, I don't know. But for the most part, these strata are not offset vertically very far. There's no huge amount of deformation in there. And again, I would take the view that it's very difficult to have the 10s to 200 kilometers of strike-slip motion through there that we know must have happened from the GPS and the relative motion history of the Caribbean's migration. So we need to look south into Trinidad, and this is the Gulf of Paria in through here. Here's the Trinidadian coastline coming down. I lost it. Here we go. We're sitting right about there, and it comes around. Southern Peninsula's down in through here. There's the Paria Peninsula up in there, and these are the blocks offshore, east and west Paria. Okay, so what we have there is a pretty curious tectonic pattern. Over here, nothing but extensional faults, and they trend northwest, southeast. And in this area, those faults cut down through the Spring Vale and go through the Manzanilla and eventually cut into the basement, if you want to call it basement. Let's call it Kush and Kuba Marine Evaporite. But it's on that those old formations where the 10 million year unconformity exists. And then above that, we have the Manzanilla and the Spring Vale, and I think eventually Talparo is the word. But you know, northwest, southeast faults, lots of perhaps east-west extension in a simple shear zone type of model. It seems to work quite well. And then we come up to the south boundary fault, and everything changes very, very much. And we go into this compressive system across the southwestern part of the island, with a couple of big exceptions. The Los Bajos fault coming in through here, and possibly other ones farther out to the southwest, such as Soldado. So there's a big change in the world right there in terms of structural style. And if we start to look at some seismic sections from in this area, this is a north-south line across that south boundary fault. It's from an area just about in here, I believe. And you can see much stronger evidence for significant strike slip types of deformation. We have things going up, we have things coming down, we have mud diapirs. And, but if you try to make a very simple pattern out of that, what it looks like is that there's a 10 million year unconformity over here somewhere with a half graben sitting in that position. Half graben happens to have some strike slip faults through it, in addition to the mud diapirs. But over here, there could very easily be one of these bounding faults that let that surface collapse to the north at about 10 million years, and then it's filled up since then. And then after all that happens, or perhaps during, lots more strike slip faulting cutting through the section. So it looks like this is a much more alive place in terms of the plate boundary. And if we apply the area balancing construction, which the class knows all about now, we can get a crude estimate for extension. This line happens to be about 120 kilometers long. It's from the flinch paper, and if you play the area balancing, you can convince yourself that there's possibly as much as 50 kilometers in that portion of it. But the base is much wider, and if you wanted to do that kind of an analysis for the whole thing, including Venezuelan data, you could easily get up to 70, 80 kilometers of east-west extension across the basin if you use a simple shear model. I'm going to have to come out of this and make it look a little bigger, if I can. This line, provided by Petrotrin ages ago, shows very well, and better than any other really, this half-graben appearance of the southern flank of the Gulf of Paria. And it's because it's in a location that doesn't have a lot of the other strike slip deformation going on. It's fairly far west in Trinidadian water. But you can see the footwall. This is North Marine Ridge up in through here. That's probably the footwall of a detachment. There's the 10 million year unconformity. And what we would have to infer from the tectonic regime that we're trying to understand is that this is an oblique slip fault. It has to have a lot of strike slip on it, because this feature in through here, if we go just to the east, this is the surface up from which these strike slip faults start to cut that section. But this shows us very well, without all that deformation, that we do have this collapsed surface that used to be at the surface 10 million years ago. Now I gotta go back.
Jim, what direction is that line?
That's a north-south line, about north 10 or north 15 east. Okay. Okay. And again, one of the ion lines in the Gulf of Paria just there shows something very similar. You can see this outward expanding wedge of material. This might be the 10 million year unconformity here. and you get the feeling that there could be a bounding fault on that side over there. And this zone in here is probably some of the strike slip deformation emanating up from the hanging wall tip of the half graben. Okay. All right, so in cross section, the whole thing could look something like this. This would be the North Marine Ridge. There's this fault detachment that we saw, and then there's these hanging blocks out in the middle of the basin. But this itself is what is extended in the east-west direction when we go to measure up all this east-west extension through the basin. And then late in the system, there's a fault system that emanates up from that detachment from the hanging wall tip, and it cuts into the Manzanilla and eventually the Springvale. And that would be the strike-slip system that defines the Warm Springs, according to some authors, or South Boundary Fault is a better term, I think, for the name of that fault. And then North Marine would be over and through here. So that's along here, and that's the fault. Okay? So we're detaching, but sliding things east at the same time. So it's classic transpression. Oh, and I have this in here to say that if we trace this fault far enough to the east, oh, that's not good. I may have to turn off the auto forward. Hang on. Yeah. I don't know why that happens, but it does. Okay, when we trace that fault east, it splays just offshore, and this would be the San Fernando lozenge, I think it was L, and San Fernando rock itself sits in that, and I think that carries on in east-west direction toward Point Radix. But the Central Range Fault Zone comes off there and splays up to the east-northeast. So this strike-slip system is what splays as we go to the east into the present-day active fault zones that cross the island. Okay, well, in very simple terms, this was a very, very old slide, but what we're talking about, I think, is here's the North Marine Ridge down here, that's the footwall. This is a transpressive collapse, where we have east-west extension in the hanging wall. At the same time, the whole thing is obliquely moving to the east, and that's giving rise to the Gulf High and the dome wall high, and the troughs between those highs out in the Gulf. So that's what we balanced to get a big number of extension, and then the main strike-slip system is coming up in that trough there. So where does it come from? If we went to the west to find the head of the Gulf of Paria extension basin, we can go into the San Juan Graben, which is up in the Serranía del Interior. The coastline is just about there in the offshore. And the seismic line there, across the San Juan Graben, looks like this. This is from PDVSA. And what we see is this high over here with early Cretaceous exposed. That's this block. And that seems to be collapsing east on well-displayed detachment faults, letting this block move that way and give the extension that gives rise to the San Juan Valley. And that section in there is that section right in there. So it looks like these normal faults are cutting through the fold thrust belt, which had just been pushed back up onto the shelf, and allowing the entire origin basically to collapse basinward toward the Atlantic. And the age of this section here is not well known, but it's quite young. I think it's mostly Pliocene, Pleistocene, all this in through here. But it fits the idea that this is essentially the head of the detachment. And if we look at the depth over here, this is 6 seconds, which might translate into, what, 7, 8, 9 kilometers. It's a very deep detachment at this position here. And that's heading off into the rest of the Gulf of Paria. And that depth of 7 or 8 kilometers is in tune with the depth conversion that the ion lines provide. So I think the depth of detachment across the basin really is that deep. So for all I can tell, we're probably down at the bottom of the fold thrust belt that had come in at 12 million years. And the whole thing is just breaking up and trying to slide out to the Atlantic. Okay, so where does that go? So we have this extension in through here. And we know, we think, we want to get to that position in Trinidad. That's the South Boundary Fault. So, although I don't have any data just in here, we would make a prediction that somehow that needs to hook up. Okay? And that would be, this is the first extensional step in this whole array of normal faults that goes all the way to the onshore in Trinidad. Okay, so where does it go? We've looked at the head. Now let's look at the tail, I guess, the front. And if we try to choose the options we have, we can come out at the El Pilar, we can come out at the Central Range, we can come out at Point Radix, or we can come out at Galeota. Those are the four primary places we might contemplate looking for strike slip coming offshore. And from this map by the Exxon guys, Stephen Butcher, it looks quite clear that it comes off of Point Radix. So Rod and I and a few other people went out to Point Radix last September at the time of the conference, and what we saw there were, let me get this right, southwest dipping beds that seemed to fit very nicely into this type of fault, although those faults existed right up and through here. And the whole section is just slumping out to the east, but the whole section had been uplifted and tilted a little bit, so the late Miocene normal faults, controlling the deposition there, was then being refolded. And that pattern of folded normal faults applies to the whole southern basin, certainly from Los Bajos east. So we felt quite comfortable that this is part of this southern extensional system with a late reactivation and an uplift probably related to this eastward migration of the northern half of the island. Okay, so that's a structure map on the top of Cretaceous, and you can see how significant that fall must be. So why is that? Well, when we reconstruct the Jurassic and Cretaceous passive margin, this is the geometry that comes out most easily. We have the Guiana transform that goes down to Demerara. We know Demerara is a rift, because when we close the equatorial Atlantic, you can jump across from Demerara into the Guinea Plateau. Northwest rifting direction, that leads to transform motion along the Guiana. And then there's another rift segment that seems to come across the southern basin. And then it relays up once more along the eastern flank of the Serranía del Interior. And people have called that the Bohordal escarpment for some reason, or trend, I think is more appropriate, because nobody's ever pointed to it. It just seems to be a fictitious difference between deep water sedimentation and much shallower water sedimentation through most of the time. And then it probably goes east-west, or maybe slightly west or south of west across the northern side of Serranía del Interior. So we have a typical serrated type of rifted margin, where the rift direction was northwest-southeast. Okay, so that means that the edge of the shelf, the main template for the margin, would fall along this heavy gray line. And we have the southern basin, which sits on a thin portion of the continental crust, and that's where the shelf probably formed. And then to the north of that, we have an essentially very deep water hole right through time, late Cretaceous, early Cretaceous, and certainly Paleogene. And I think the reason that the southern basin is entirely pelagic until, well, Middle Miocene time, really, as compared to the clastic depositional system is because of this reentrant. And we know that the Serranía del Interior was very, very clastic in the Paleocene, Eocene, and Oligocene. And it's not too difficult to envision how plastics may have come off of that shelf down into the deep water there and bypassed the southern basin. I think that much seems to be pretty clear. So that template works well when you make a reconstruction with Yucatan and the Bahamas, and everything fits back together quite nicely. But now let's think about where this strike slip goes off to the east. We could look first up at the North Coast Fault Zone. This is the basement surface of the Tobago terrain. It goes up to the island of Tobago right about there. This is the North Coast Fault Zone. It really looks like nothing more than a half graben. And if we can zoom in on that. I think you're pressing your luck to put a huge amount of strike slip through there. There's certainly some normal displacement, but it's difficult to cut the young section, certainly. Another option is Galeota Point, and we can go down there and look at that. And what we see there is, this is a setting where we have refolded some of the normal faults that are late Miocene and Pliocene in age. So you end up with an antiformal stack, but the bed forms are fanning because it had previously been a growth fault, perhaps at that surface there. But still, that section is deforming, surely, but there's not a lot of strike slip motion through it. Another place is at the Central Range. Let's think about that. What we see there is possibly 3 zones of faulting. Yes, it's certainly active, but the remaining one to look at is the point radix. And in terms of the most amount of uplift from either side, with the deformation right at the surface today, and completely obliterating any structure that you can see inside of that, this is probably the strongest deformation. And I know that's a dangerous thing to say, but it certainly looks more intense than the other ones. So I think that there's good evidence that the point radix fault has to be probably the primary fault system crossing Trinidad, and this is meant to be sort of a synthesis of the main shear zones for the last few million years, last 10 million years. The blue ones have all been active since about 10, and then the other ones, San Juan Graben and the southern anticline, and possibly Galeota, have been compressional since about 3. Up north of this blue system in through here, this is the main east-west detachment cutting up the origin, which formed in 12 million years, so it's all heading out to the east. But what about that yellow? I looked at the mud diapier trends a few years ago with PDVSA over in Maturin, and these are the mud diapiers in that area. This is San Juan Graben coming down from the north, and these are active mud diapiers in sort of east-west linear systems. If I just go off the page here a little bit farther, you're at Pedernales, and I think you can see this. There's the front of the Serranía del Interior with big folds. That's the wedge top basin. There's the foreland over here. That's meant to be the 10 million year unconformity there. And then here's this younger section above that that has really no compression in it other than the mud diapiers themselves. And even if those are compressive, and I don't know if they are, you know, the amount of compression is I don't know, 2, 3, 4 kilometers. You know, it still supports this idea of east-west shear, giving rise to the conduits up which the mud can flow. One of the models we'll be considering on the field trip tomorrow is a simple one like this, where you call it a fault propagation fold from possibly a little nudge of the fold stack at Soldado to the south, or to the north, and maybe that gives rise to the conduits that lets the mud volcanoes up along the south coast anticline. So that could be, it looks very similar to Pedernales, it looks very similar to Eastern Maturin Basin. The other fault that was on that map, and unrelated to the Gulf of Paria extension, is the Los Bajos. And what we realized working with Petrotrin, I don't know, some number of years now, the Soldado stack is this main field. The 10-5 uniformity is up here like this, but the 10-5 just to the northeast is over here. And there's a big detachment system between this area here and the thrust stack of main field. Now we saw this on about, I don't know, 15, 20, 25 arbitrary lines in the 3D survey in the offshore. Now I have never looked at this in the onshore, so I don't know if these comments apply to the onshore portion. But it looked to us that what people have always called Los Bajos is really fairly insignificant compared to this larger architecture that sits below. So a few years ago we started using the term the deep Los Bajos versus the shallow Los Bajos, and just like in the Gulf of Paria, the strike slip faulting and other transgressive types of deformation associated with Los Bajos seems to emanate up from the hanging wall tip of this half graben. So again, we would have to, if we wanted to acknowledge the strike slip that people have argued for forever on Los Bajos, we could put that in here, whatever it is, 11 kilometers apparently, or something approaching that. That has to cut up through the section that fills as this is forming as an extensional detachment. So I don't know when it turned on. We could form the bulk of this basin without faulting, and maybe it turns on quite late. I don't know. But it looks very much like the southern flank of the Gulf of Paria, in that the strike slip emanates up from the hanging wall tip of the half graben. So we mapped this quite a lot, and I don't think I have the structure contour of that map, but we were able to make a structure contour map of that detachment surface. So this is the idea. We're up above the fold thrust stack of the middle Miocene, so that's going to be down here somewhere. And then cutting across the thrust stack is a transtensional fault, which lets the hanging wall drop down with respect to the regional over here. And then we get this half graben, and that's an ideal place for the Herrera sandstones to have come down from the northwest. So going all the way back to the start of the talk, trying to understand how we could get detritus from the northwest portion of Serranía del Interior in Venezuela down to Galfa Point. This is probably the way it was achieved. Okay, so we can trace that down, and if you look at a map, that is directly north of Galfa Point. So, okay, so that's 15 to 10 million years. We've got this half graben geometry. Any kind of an oblique collision has got to have axis parallel extension taking place at the same time the thrusts are in placing. So that would be the origin of that structure at that time. And you can see one good thing about this, that structure is cutting all the way down to the base of the origin. So you know that fault has to cut across the entire maturation kitchen, even back at that time, and it still does today. All right, so that the trough fills up then with Cruz. On the southwest side of Los Bajos, the convention is to call it Cruz. To the northeast, it's Manzanilla. But then at about, whenever that is, 3.5, maybe 2.5, maybe 1.5, I'm not sure, it becomes active again. And at about the same time, the southern range happens, and we have this tightening of structures all across the rest of Trinidad. So something is happening very recently that is different to what happened between 10 and 2 or 3 million years. So we can go back to 10 million years. We can make a gross reconstruction of the main orogeny at that time. All I've done is push the Caribbean plate back 200 kilometers. And that puts the leading edge of the crystalline crust in through here. There's still a lot of accretionary prism out in front of that I haven't shown here. Just ignore that. And that crystalline edge then, it looks to me like it has to come, there's Tobago. Looks like it has to come under the northern range. It comes under Paria and Araya. And it actually probably emplaced a wedge underneath the sedimentary section in the northwest portion of the Serranía del Interior. And that's why the oldest rocks there are exposed at the highest level, all the way down to the Belgian, unlike anywhere else in the whole mountain front. Okay, so then on top of that oblique collision, we can superimpose the east-west shear system that takes place when the relative motion changes. So we'll cut through over here. That's called the Morone Fault to the north of Caracas. It steps obliquely down to make the Gulf of Cariaco pull-apart basin. Then it comes across to the south of Araya Paria and also pushing in toward the eastern end of Gulf of Paria. There's the northern range there. Northern range has to get over there. So I'm pretty comfortable feeling that the Caribbean plate has wedged under the northern range, and it's a northwest back thrust really of material back up onto the top of the Caribbean plate, and that's why the northern range moves at the full Caribbean velocity to the east with respect to the shield down here. But that makes all of the strike slip since 10 million years go through the middle of Trinidad, and I pretty firmly believe that. We can look at the seismicity. Fortunately, Venezuela gets the bulk of that, and for some reason, we can see the El Pilar fault coming along in through here. It's very active. Certainly, the San Juan graben is active, and then it starts to come across the south boundary fault, and it seems to stop right at the boundary. Magic. My hands are up. I don't know what to say about that, but I think we do understand the geometry of the plate boundary there, and I'll come to that next. But for some reason, this portion of the plate boundary seems to be lubricated or locked. And I don't know the answer, and I don't have any preference in those two possibilities. I'm not an earthquake person. So to summarize what's going on, and has been going on for 10 million years, we've got this bow wave that we call the Caribbean Plate. It comes around with a curvilinear southeastern flank. We can push it back 200 kilometers to approximate 10 million years. And that would take it back to about there. So the flank of the boat at that time is entirely north of the Serranía del Interior. So that would explain very nicely why we don't have any further deformation in the Serranía or the Maturin Basin. We will have compression out in front of the curved part, so Trinidad's going to see some more compression. But with time, this nick point between the bow and the flank of the boat is going to migrate, and right now it sits under, I don't know, 11 teal. So we still have compression forming out in through here, which is clear on the seismic, but the Gulf of Paria has no compression. So I don't know when the point, change that around. I think we can map the migration of this point quite well, but the deformation to the sediments in the basin is up to, in terms of being able to date that deformation, we have to know the age of the sedimentary fill. And to my knowledge, we don't know if Manzanillo is 10, 9, 8, 7, maybe even 6. So perhaps the bulk of the Gulf of Paria could be on the side of the boat before the bulk of that deposition has even occurred. So in this way, if we look at what happens in a cross-section like this, trying to understand Trinidad, here's the onshore portion that matches here. We can look at the 10 million year position, it's over here, and the 8 million year position is here, and the 4, and then the present. Okay, so the wedge, that's the Caribbean forearc, is coming in, and even though it's moving east-west, it still is approaching Trinidad in this cross-section because of the shape of the boat. So we're putting more and more and more of a load onto the Trinidadian flexural beam as the Caribbean plate moves east. But it's not making any compression on the side. So for as long as this plate keeps thickening downwards, we're going to continue to add additional load onto the flank in here, and that will continue to drive the top 10,000 feet in the Maturin Basin with no compressional faults, and it will continue to drive the Sapero, well, not Sapero, I guess Cruz and Forest, and all the other young section of the southern basin in southern Trinidad. There should be a southward onlap out to a nick point, which is very close to the Orinoco River today, and this additional accommodation space above the heavy blue line is the foredeep, even though there's not very much compression in it. So it's a lateral application of an orogenic load. It's not an orogenic load, it's a plate load, it's the Caribbean plate. So we're getting a whopping great substance with very little evidence for compression. So what turns on this late compression at 2 or 3 million years? I don't know for sure. I guess we could play games and try to change the direction of the Caribbean plate, but the GPS does not support that. It's something we used to be able to think about, but now we can't. So that doesn't seem to work. What we do expect, though, is that the basement structure contours going down underneath the Caribbean plate will basically try to match the shape of the Caribbean plate itself. So the strike portions of contours are going to be running about like this, and the plate will be deepening that direction. So if the hanging wall of the origin is moving due east, trying to climb up a basement surface that dips to the northwest, that will impart a compression. It's an oblique, transpressive, regional compression across the entire thing. And as we've seen, we have inversion taking place on east-west faults. We have inversion even on Los Bajos. We have the diapir system working all the way over into the Maturin. So whatever's happening right now for the last 2 or 3 million years, it's a regional thing, and I think it takes something as regional as the attitude of the basement to make all those things happen everywhere. You can't just blame it on a releasing or restraining bend on any of these individual faults. So that's probably what it is, and I guess in cross-section, I think the last slide is this one. And this is just what Lorcan Kennan and I came to at the end of our study. Northern range is sitting up in through here. In some of the IL lines, you can actually convince yourself that there may be a wedge underneath the northern range itself. The leading edge of the Caribbean plate could be as far south as Caroni Basin. And the faults coming up from between the Caribbean plate and the South American basement come up into the central range and through this area. And then some of these are telescoping to the south and giving the late compression on the south coast anticline. So 12 million year compression, then a transtensive relaxation, and then a poorly understood driving force, but still a tightening up of all those structures in the last 2 or 3 million years. Right. So I think I would like to close by paying a little tribute to this guy, John Frampton, who has, well, he probably had 30 years here, 40 years here, I don't know. Maybe 50. Well, he and Barry Carr Brown, who I wish was also in this picture, contributed as much as anybody to our understanding of Trinidadian stratigraphy, and it's largely to them that we're able to synthesize some of these tectonic stories that we've come up with in the last few years. And you know, a lot of this has been in very close association with both of those guys, so I'm deeply indebted to them. Frampton is home enjoying retired life in Dorking, only about 15 miles away from me, so we hook up every little bit, and he still enjoys his beer. Thank you very much.